Welcome to Z-score. So the idea here is we want to essentially standardize how we talk about where a data value falls in relation to the mean. So we want to standardize how we talk about where a data value falls in relation to the mean. And the way we'll do this is we'll look at how many standard deviations away a data value is. So the formula that we reduce this down to is that z-score, or z, is equal to the data value x minus the mean divided by, x minus mu divided by the standard deviation sigma. Again, this is really the data value minus the mean divided by the standard deviation. And what this is doing is this is calculating, this is the number of standard deviations above the mean. So if we consider this example, the mean score in an exam was 82. So we have mu is 82 with a standard deviation of 6. So sigma is 6. We want to know what z-score corresponds to an exam score of 88. So an exam score of 88, they're telling us the data value we are looking at. So that's x is 88. So if we looked at a number line, the mean is 82. And if we go up by one copy of the standard deviation, so one copy of 6, that would put us right at 88. Right? So in this case, 88 is one hop above the mean. It's one complete standard deviation above the mean. So we would expect a z-score of 1. So this is 1 standard deviation above the mean. And if we do our z-score calculation, z equals, we should do the data value x minus the mean divided by sigma. So we are looking at 88 minus 82 divided by 6. That's 6 divided by 6, or 1. So our data value was precisely 1 full standard deviation, 1 full hop above this mean. So our z-score is precisely 1. So our z-score is 1. Now if we do what z-score corresponds to an exam score of 73, here's our 82. If we go 1 standard deviation below the mean, that would put us at 76. If we go another standard deviation below the mean, that would put us at 70. And we are looking for 73. So it turns out 73 is precisely 1.5 hops. So 73 is 1.5 hops, or 1.5 standard deviations below the mean. But again, we can use the z-score just to calculate this without having to figure out the hops. So we have z is x minus mu divided by sigma. X is our data value, so 73 is our x. We are looking at 73 minus 82 divided by 6, or negative 9 divided by 6, and we get negative 1.5. So this is 1.5, but negative. Now the negative tells us that we are actually below the mean. So z-score calculates the number of standard deviations above the mean, and negative z-score just means it's below the mean. So a negative z-score means that it's below the mean. Other than that, the z-score is just telling us how many hops we have to go away from the mean, where each hop is a full standard deviation. So this is the general concept of z-score. The reason why it's great to standardize is some data sets are much more spread out than other data sets. And so if we just go by distance, we lose track of sort of the spread of the data set. Once we do this standardizing, we take into account both the mean and how spread out the data is. So in this next example, we have Alejandra scored 32 on an exam in class A, and that class had a mean score of 28 and a standard deviation of 5. Brian scored 81 on an exam in class B, and that class had a mean score of 75 and a standard deviation of 10. And we want to know which student scored better in relation to their class. So let's have two data sets, or two things going. So we have Alejandra, and then we'll have Brian. So for Alejandra, class A had a mean of 28 and a standard deviation of 5. And we are told that Alejandra scored 32. And we want to know what z-score corresponds to that data value. Brian, on the other hand, the mean for his class was 75 with a standard deviation of 10. His data value was 81. And again, we want to know the z-score. This way we standardize these and we can compare two data values from two completely different data sets with different means, different standard deviations, but we can still compare how they are in relation to their class. So for Alejandra, we can do our calculation. Z is equal to x minus mu divided by sigma. So we are looking at 32 minus 28 divided by 5. This is 4 over 5, otherwise known as 0.8. So Alejandra's score is 0.8 standard deviations above the mean. Brian, on the other hand, we have z equals x minus mu divided by sigma, or 81 minus 75 divided by 10. This gives us 6 over 10, or 0.6. So Alejandra scored 0.8 standard deviations above the mean versus Brian only scored 0.6 standard deviations above the mean. So this is more standard deviations above the mean. And so that means that Alejandra scored better relative to her class. So despite the fact that Alejandra only scored 4 points above the mean, whereas Brian scored 6 points above the mean, once we take into account how spread out the data is, Alejandra scored better. All right, that is Z-score.